Alright, so this first one is about a differential equation. Alright, so they give us this differential equation, and just to review, remember, solutions to differential equations are functions, right? It's like you have this one function that you're taking you're on the left hand side you're taking the derivative of some function y, and the right hand side you just have y kind of somewhere. But you need some function that if you take the derivative, that would end up being the left hand side, so you take the derivative of that function. It's the same thing as 10 minus 2 times that function. So that's what we're looking for. We're looking for some function that if you plug it into this differential equation, makes both sides the same. Alright, so first one says write an equation for the line tangent to the graph of y equals f of x at x equals 0, and then use that tangent line to approximate the function at 0.5. Alright, so to get the equation for the tangent line, we need a point and we need the slope. Okay, so we know that at x equals 0, there's the point 0, 2. So we know the whole point is 0, 2. And then here, so this gives you the slope. This gives you the derivative of y, right, at any point. So notice this derivative is only in terms of y. So if we plug in the y coordinate of this point here, so whatever the y coordinate of the point is, plug it in here, and that'll be the derivative at this point. And then the derivative of that point at that point is the slope of the tangent line at that point. So that'll be the main thing to do. So we'll take 10 minus 2y, plug in the point 0, 2, which is really only plugging in the y value. And so that's 6. Okay, so we have this slope of the tangent line and this point, and then notice this point is like the y-intercept, 0, 2. So really 2 is b if we're going to use y equals mx plus b. So our approximation, tangent line approximation, is y equals 6x plus 2. And then now we can plug in 0.5 into that. Okay, so if you plug in 0.5, that's 5. Okay, so that means f of 0.5 is about 5. Okay, next one, find the second derivative at the same point. Okay, is the graph of y concave up or concave down at that point? Okay, so let's take second derivative. Okay, so we have the derivative up there. So I'll rewrite this. Okay, if we take second derivative, this is just negative 2 times dy dx. Okay, we already know dy dx at that point from the previous one is 6. So this is just negative 2 times, actually here. Okay, and then notation, so we're going to plug this, we're going to evaluate this at the point. And then this is negative 2 times 6 is negative 12. Okay. All right, and then this this is the second derivative, and the second derivative is negative, so that means it's concave down. So just write a little sentence. Maybe f of x is concave down at 0, 2, because the second derivative is negative. Okay, next one. Find the particular solution to the differential equation with that initial condition. Okay, so finding particular solutions are about integrating, and so we haven't done this in a while. I don't think. Okay, almost always with these, before we integrate, we're going to separate the variables. So here we have a dy on the left-hand side, and we need to get this y on the left-hand side with it. And then the dx will go on the right-hand side. If there were other x's, we'd keep them on the right-hand side also. So we basically just want any kind of y on the left-hand side and any x on the right-hand side. The only thing is you can't really add to both sides. Like, we can't add 2y to both sides. One thing, we'd end up with a problem you'd see of, like, now moving dx to the other side becomes kind of impossible, because you have to multiply by dx, and then the 2y would get multiplied by dx. Yeah, so anyways, and so really you always want to kind of multiply and divide to get variables on a different side of the equation. So basically, and the only way to do it is to divide this whole thing to bring it here, and then multiply this dx to bring it over here. And so we can just kind of do this. We end up with dy over 10 minus 2y equals dx. And then that we're going to integrate. So now this we can integrate. Okay, so I'm going to kind of do this one. So this integral is going to be an ln. We know it's going to be some kind of a ln of absolute value of 10 minus 2y, something like that. But if we take the derivative, we'll get 1 over 10 minus 2y like we want, but we'll end up getting, it'll be multiplied by a -2 because of the chain rule. So just multiply this by -1/2 to get rid of that. Okay, so that's the integral left-hand side. Integral right-hand side, integral dx is just x, and then we'll have this plus c. Okay, so now we need to do two things. Find c, and then solve this for y also. All right, so we'll find c by plugging in the initial condition. So we'll plug in this point 0, 2. Okay, so I'm going to do that now. Okay, so if you plug in 2 for y, you get ln of 6. And then plug in 0 for x, just get c. So that's just what c is right there. Okay. And then now we'll solve this for y. So now we can plug c back into this, and then solve for y. Okay, now we just have to solve this for y. Whoops, why would I do that? I don't know. Just that, okay. Yeah, okay, so now solve this for y. I'm going to multiply both sides by -2 to get rid of this -1/2. Okay, and then raise both sides to the e, make that to the e, and this whole thing to the e. Each of these is to the e. Okay, the e and the ln cancel. Again, we don't need those absolute value anymore. And then the right hand side, so we have e to this whole thing, and I'm going to split it up. We can rewrite it as e to the negative 2x times e to the ln 6. Okay, the e to the ln 6 is just 6. So we can rewrite this. 6 e to the negative 2x. And then just start solving that for y. Do that here. So you're like minus 10 to both sides. And then divide both sides by negative 2. Okay, and that's it. So that's the particular solution to this differential equation. And you can see if you took this function here of what y is, and if you plugged it in to the differential equation here, plugged it in for y there and then for y there, so you take the derivative, then if you did that, both sides would be equal. So, okay. So that's our particular, okay, and then they say for the next part, they say for the particular solution that we just found, find the limit as x approaches infinity. Okay, we'll do that. Okay, and then so as that approaches infinity, this whole exponent approaches negative infinity. And then if this approaches negative infinity, if you have e to the something and the exponent approaches negative infinity, this whole exponential will approach 0. And so this is really just negative 3 times 0 plus 5, which is just 5. Okay, so that's everything for that problem. Okay, so this next one looks like it's a kind of related rate, maybe. Yeah, okay. Okay, so they say for t between 0 and 6 seconds, a screensaver on a computer screen shows 2 circles that start as dots and expand outward. Okay, at the instant that the first circle has a radius of 9, the radius is increasing at the rate of 3/2 centimeters per second. Find the rate at which the area of the circle is changing at that instant. Okay, so for the first circle, when the radius is 9, this is just at a single moment in time. When the radius is 9, it's changing at the rate 3/2, so dr dt is 3/2. And then they want us to find the rate at which the area of the circle is changing. So we know that area is pi r squared. Oh, and just keep in mind we're looking for dA dt. Okay, so now we take derivative of both sides of this area equation. So dA dt 2 pi r dr dt. And then now we can just substitute our values. R is 9, dr dt is 3/2. And that is 27 pi. Okay, don't forget units. This will be square centimeters per second. since this is change in area, it's got to be square centimeters, and this is per second. Okay, next one. The radius of the first circle is modeled by that now. Okay. Where WT is measured in centimeters and T is measured in seconds. At what time T is the radius of the circle increasing at a rate of 3 centimeters per second? Okay, so we want to know, yeah, so at what time is the radius increasing at 3 centimeters? Okay, so this is the radius. This is a function that you plug in any time and it tells you what the radius of the circle is at that time, from as long as it's between 0 and 6. Okay, so we want to know when the change of this equals 3. So we really want to know when the derivative of this equals 3. Okay, so take derivative. Okay, 12 goes away. So this will be negative 12 e to the negative 0.05 t, and then times the derivative of the exponent, just negative 0.05. Okay, and this equals, or negative 0.5, not 0.05. And then that equals 6 e to the negative 0.5 t. Okay, and we want to know at what time does this equal 3. Okay, so we set that equal to 3 and solve. So divide by 6. And then take ln of both sides. And so the left-hand side just becomes negative 0.5 t. ln of the right-hand side, ln of... I'm going to rewrite this half. I'm going to rewrite it as 2 to the negative 1, like that. Okay, that way we can do 0.5 t equals, and then we can bring the negative 1 out, that. And then these negatives kind of go away now. And then divide, or really times both sides by 2. So you get t equals 2 ln 2. And you could rewrite this as ln 4. That would be the simplest way to write it. Okay, probably though, I mean, it doesn't really matter. You know, shouldn't simplify, but this, we know that this is right, so this is not too bad. Okay, and so that's the time. And this will be seconds. Okay, last one for this one, this problem, this section. Yeah. So a model of the radius of the second circle is given by the function f, where f is measured in centimeters. Okay. T is measured in seconds. Okay, the rate of change of the radius of the second circle is given by that derivative function. Okay, based on this model, by how many centimeters does the radius of the second circle increase from time equals 0 to time equals 3? Okay. Okay, if we're given a rate function, you know, and here this rate is about the radius, and it's how much the radius changes per second. When you integrate, when you integrate a rate, you know, here this will be, you know, this radius is measured in centimeters per second, and so, and this is centimeters of the radius, you know, how many centimeters long the radius is. And so if you integrate this function, you'll get the total change in centimeters of the radius. And that's what the question asks. By about how many centimeters does the radius of the second circle increase? What's the total increase of the radius from t equals 0 to t equals 3? And so that's what we'll do. To find that total increase, we'll integrate from 0 to 3, just this function here. So just try to be careful. Nice thing when we plug in 0, everything just becomes 0, so we don't have to do that. So just really plug in 3. Okay, so t cubed over 3, if you plug in 3, you just get 9. And then that'll be minus 18 plus 12. That is 3. Okay, so the total change in the radius was 3 centimeters. Okay. Okay, so the next one says let f be an increasing function. F of 0 equals 3. Okay, so they're saying it's always increasing, and then they give you the derivative of f. Okay, so just realize that they're saying that this is always positive, and we probably could have figured that out. Maybe not actually, but this is always positive. Since the f is always increasing, derivative will always be positive. Okay, so they asked us first to find the second derivative at negative 3. So we'll just take derivative of this function. Negative pi, so sine pi x plus 4x cubed. Okay, and then we'll plug in negative 3. Okay, so sine of negative 3 pi x, or negative 3 pi, sorry, is 0. Sine of any multiple of pi is 0. And so we just really have to plug in negative 3 into here. So that'll be 4 times negative 27, which is negative 108. Okay, next one. Okay, write an equation for the line tangent to the graph of this new function, which is the square of our original function. And we want to find the equation for the tangent line at x equals 0. Okay, we have the full point. Well, do we? Well, we know f of 0 equals 3. Oh. So yeah, if you plug in, if f of 0 equals 3, then this function at 0 is 9. Right, since it's really our original function squared. So we really have our point is 0, 9. All right, and then now we need to find the derivative of this at 0, so that'll be the slope of our tangent line. So y prime derivative is 2 f of x times f prime of x. Evaluate this at 0. this is 2 times f of 0 times f prime at 0. Okay, f of 0, they told us is 3. Yeah. Oops. Okay, so f of 0 is 3, so it'll be 2 times 3. And then times that by f prime at 0. So here's f prime. If you plug in 0, this is 1, this is 0, and 6, so that'll be 7. Okay, and then this will be 42. Okay, so that's our slope. Okay, so equation for the line tangent will be y equals mx plus b. Okay, next one. Alright, so take derivative both sides to find g prime at 3. So first we'll find g prime of x. Okay, so remember with chain rule, we'll take the derivative of the outside, leave the inside alone, times that by the derivative of the inside, and we'll rewrite this. So now the derivative of that, when we do the chain rule, we'll get a 4x, and that'll be times by a half, so that'll really be a 2x. And then it'll be this whole thing to the negative 1/2. Okay, so we'll do that. So now we'll plug in 3. If you plug in 3 into this inside part, it's 25. This will be 18 plus 7. This is f prime of 25. Okay, plug in 3, that 2x will become a 6. And then this will be, if you plug in, so this is 25 to the negative 1/2, which is 1/5. Okay, so now we got to figure out how to evaluate that f prime at 25. And so we've got this. Got this up here. Wait. Oh no, that should be f prime at 5. Sorry. Something was weird. Square root of 25. Okay, and then so f prime at 5, so we'll plug in 5 into here. So here, if we plug in 5, cosine of 5 pi is negative 1, and so plus 6, that'll be a 5. So, and then 5 to the 4th is 625, and then plus 5 is 630. So that's really 630. Divided by 5. Okay, and then that is that's 126 6, and that is 2756. Okay, last thing. Let h be the inverse of f. Find h prime at 3. Okay, so there's a formula. So if you want to find the inverse of another function at some number, so keep in mind you have this here, sorry. So f of 0 equals 3. You have this thing f of 0 equals 3. Okay, if h is the inverse, that means h of 3 equals 0. Okay, and so that means if you have a point 0 comma 3 on a function, then you have the point 3 comma 0 on the inverse. It's like, I think it's the definition of inverses, where you switch each point and it now becomes a point on the inverse, or it is a point on the inverse. Okay, but the formula says if we want to find the derivative of a function, and we only know its inverse, so we can say h prime at 3 is the same as 1 all over the inverse function, its derivative at the other coordinate. So here, if we want to find h prime at 3, we'll plug in 0 into the inverse, like that. Okay, and then, did we already find f of 0? Or f prime of 0? No. Okay, so f prime of 0, we can look up here. Cosine 0 is 1 plus 6, so that's 7. And so that's it. Oh, so whoops. That'll be really 1 over 7. That's it. Okay, so for this one, it says a particle moves along the x-axis and the position is given by this function for values of t between 0 and 2 pi. Okay, from the time that t, or find the time t at which the particle is farthest to the left. Okay, so you just really want to know when the position is the biggest negative. So when you're wondering when is this function, you really just want to know what's the minimum value of this function on this interval. So this just becomes one of those types of questions where they're asking what's the global max or min of a function, or the absolute max or min of a function on an interval. Okay, so to do that, you take derivative, find critical points. X prime at t. So this happens to be the velocity, but it's not important for this one. So we'll just take derivatives. So we'll do product rule. So I'll do the derivative of e to the negative t first. Psi t plus, and then e to the negative t times derivative of sine is cosine. Okay, so we want to know when, what critical values this has, when this is 0 or when this is undefined. Okay, so now we can pull out an e to the negative t, maybe. And if we do that, we end up with, I'm going to switch these around, cosine minus sine. Okay, and this is never undefined, so we really just want to know when this equals 0. Okay, exponentials never equal 0, never undefined, so this part doesn't even matter. Don't even care about that. So we really just want to find out when this is 0. And if you think about it, this is going to be 0. When I find when this is 0, if you add sine to both sides, or just think about it, this is 0 when cosine equals sine. And then you just really have to think unit circle. Where does, on this interval, just on the unit circle basically, where does sine and cosine equal each other? So that's at like the over 4s, pi over 4. The first quadrant, and then wait, why are they both negative? So like 5 pi over 4, I guess. Third quadrant, they're both negative. Yeah. Okay. So we got those two critical values, and then now we'll take those and the endpoints and plug those back into the original, and then see which one's the smallest. So just kind of do that off to the side. So we'll do x of 0, x of pi over 4, x of 2 pi. Okay, plug in 0, you get 0. Plug in pi over 4, you get e to the negative pi over 4 times sine of pi over 4, which is root 2 over 2. Okay, so who knows what that is, but some positive number at least. Okay, plug in 5 pi over 4, then you get e to the negative 5 pi over 4, and then sine of 5 pi over 4 is negative root 2 over 2. Okay, so that's the first negative number, so that's probably the answer. And then if you plug in 2 pi, sine of 2 pi is 0, so that's just 0 again. Okay, so it's this. That gives you, that's the smallest value. Yeah, so this is the smallest value. And they say find the time t, and so 5 pi over 4, that's the time where it's farthest left. So t equals the biggest negative, and so that's farthest left. Okay, so this one says, starts off, during a chemical reaction, the function models the amount of a substance present in grams at time t equals time t seconds. So this function is the amount of a substance present at any given point in time. Okay, at the start of the reaction, there's 10 grams of the substance present. Okay, so there's 10 grams initially. The function satisfies this differential equation. Okay, use the line tangent to the graph of f at t equals 0 to approximate the amount of substance remaining at time t equals 2 seconds. Okay, so we had a similar problem earlier, or another, question 2 or 3 was the same, or maybe 1. I think 1 actually. Okay, so now we want to, okay, so at time t equals 0, there's 10 grams. So 0 comma 10 is a point on the function, and now we just need the slope. And to get the slope, we'll plug in, to get the slope, we want to know what the derivative is at 0. So when t equals 0, y is 10, and so if you plug in 10 into that derivative, so dy dt at t equals 0. Negative 0.02, and then when t is 0, y is 10, so this is really 10 squared. And so it's 100 times negative 0.02, and that's just negative 2. Okay, so now that's going to be the slope of our tangent line. So use a tangent line to approximate. Okay, so the tangent line equals negative 2x, negative 2t, and then plus 10. 10's our y-intercept, so that's b. Okay, now we'll evaluate this at t equals 2. Plug in 2 to that, and you get, and you get 6. That's 6 grams. Okay, so don't forget units when you need them. Okay, make sure. Yeah, okay. Okay, use the given differential equation. Using the given differential equation, determine whether the graph of f could resemble the following graph. Oh, I need to put that graph in there. Here, 1 second. Okay, so here's the graph. Okay, so using the differential equation, determine whether the graph of f could resemble the following graph. Okay, the only real qualities we know is it has a positive y-intercept. We know it's initially decreasing, and it decreases for some amount of time and then starts increasing. And it increases before it becomes negative. Yeah, so those are the kind of the only things we know. So we'll really try to kind of disprove one of those things. So the y-intercept is definitely positive because 0, 10 is a point on the function. It is initially decreasing for sure. Well, yeah, because it's initially, y is initially 10. And so if you plug in 10, initially this is -2, and so that looks like about right. And then they're wondering, and then does this ever start increasing again? And the question is this ever positive? Which is no, right? Since y squared is always positive, you're really doing a negative number times a positive number. That's always negative. So according to the differential equation, this function's always decreasing. Okay, so that's our answer. Using differential equation to determine whether the graph. So say something like the graph f could not resemble the given graph because since the derivative of f is always negative, f is always negative, it should always be decreasing. But the given graph increases. At some points. All right, something like that. Okay. Next one. Okay, find an expression for y by solving that differential equation within that initial condition. Okay, so now we got to separate variables. This constant you can either bring over here or you can leave it over to the right. I'm gonna leave it over to the right. So I'm gonna divide by y squared. Leave that constant to the right and then multiply by dt. And then this is what we'll integrate. We integrate both sides. Okay, left-hand side is negative y to the -1. Just integrating y to the -2. Right-hand side is -0.02t. And then plus c. Okay, we know the initial condition when t is 0, y is 10, according to this. So we'll plug in the initial condition. Yeah, so just so you know, we can plug in the initial condition now, or we can solve for y first, and then plug in the initial condition to solve for c. I'm going to do it now, it doesn't matter. Okay, so this is, so y is 10, so this is negative 10 to the negative 1, which is really negative 1 over 10. And then t is 0, so this is really just c, right, like just like that. Okay, so now take this and plug in c, so we have negative. So now we'll just rewrite this, but with negative 1/10 plugged in for c. Okay. And then keep in mind, if c is negative 1/10, that means everything's negative, so I'm just going to change everything to positive. And then this will be 1 over y. So 1 over y equals 0.02 t plus 1/10. Okay, and then you could do this different ways. The probably safest way is just take, kind of think of this as over 1, and then take reciprocals of both sides. So that would be the safest bet. Okay, so that could be an answer. If you want to, do we have to use this? Let's say we had to use this in another step. We probably wouldn't want to leave it like that. And so the way to do it would be to find a common denominator in the bottom. So this would be like 1 over 0.02 is 1 over 50. This would be like t over 50 plus, and then 1/10 is like 5 over 50. And then now we can see this is 1 over t plus 5 over 50, and then that's just a reciprocal. Okay. And so you could either put this as the answer, or put that as the answer. Sorry, I want to check answers as I go. Yeah, that's right. Okay. Okay, last part. Determine whether the amount of substance is changing at an increasing or decreasing rate, and then explain your reasoning. Okay, if we want to know if changing at an increasing rate, do they mean like just first derivative is 0? Or do they mean like second derivative, or first derivative is positive or negative, or do they mean second derivative positive or negative? Let me think. Okay, so they want us to really talk about the second derivative. So they want to know how it's changing. Is the changing, how the changing is changing? Is the changing increasing, or is the changing decreasing? Okay, yeah, that makes sense. Kind of. All right, so we have our first derivative already. Negative 0.02 squared. Okay, if we take the derivative of this, it's negative 0.04 y times dy dt. Okay, and we want to evaluate this term whether it is increasing, whether the is changing at an increasing rate. Okay, and then dy dt here is this, so I'm going to plug that back in. That's times negative 0.02 y squared. Okay, this is going to be positive 0.0008 y cubed. Okay, and then since let's see. Oh yeah, since y is always positive, you know, this represents the amount of substance. So that means it really has to, you know, has to always be positive. We could see even by, so this y is the same as this y, and for positive t values, this is always positive. Okay, so that means since y is always positive, that this function's always positive, right? This second derivative, that means the function is changing at an increasing rate. Always. The substance, since this second derivative is always positive, the substance is always changing at an increasing rate. This would be like the final answer for that. Okay, so that's everything. Okay, so this next one, consider the family of functions, okay, where k is a constant. Okay, so family of functions, because this function has an infinite number of possibilities, because k could be an infinite number of numbers. So, and each different value of k kind of creates a slightly different function. So that's what they mean by family of functions. Okay, find the value of k, where k is positive, such that the slope of the line tangent to the graph of f at x equals 0 is 6. Okay, so they really want to know, if they want to know where, they want to know where they want to know value of k such that the slope of the tangent line is 6 when x equals 0. It means the derivative should be 6 when x equals 0. So we'll take the derivative first. Okay, this is a weird one. I don't know what's better to do, quotient rule or power rule. I actually don't know. So let's say if this was, we could change this to like that and then just do power rule and chain rule. I'm gonna do that actually. But I think quotient rule, I think it's probably just about the same. It's negative, keep the inside the same. Negative 2 and then chain rule. Okay, so now when x equals 0, this should be 6. So we'll evaluate this when x equals 0. Okay, when x equals 0, this is negative k to the negative 2 times negative 2. Negatives cancel, so this is really just 2 over k squared. And this should equal 6. Make sure about that. Okay, that means k squared should equal 1/3. So that means k technically equals plus or minus square root of 1/3, but they say k is always positive. So k just equals square root of 1/3. Yeah. Okay, and then you could write it as square root of 3/3. Same thing. Okay, so next one for k equals -8. Find the value of that. So, okay, so plug in -8 and then take the integral. Right? Yeah. Okay, so definitely going to do partial fractions for this. So we're going to do a bunch of scratch work over here, and then we'll come back to this in a second. So this is like, so first we'll factor this, x minus 4, x plus 2, this, and then this will be a all over 4 plus 2. Okay, and then just remember we'll basically kind of start adding these, find common denominator. So this is the common denominator. So we'll have to times top and bottom by x plus 2. And then this one will times top and bottom by x minus 4. So it'll really be a times x minus x plus 2 plus b times x minus 4. And for this one, I'm showing more work than I need to. But just to realize that now that if you see this and this, they have the same denominator. So in order for them to equal, this has to be 1, So really we're just going to set this equal to 1. And then when we set this equal to 1, we'll also regroup this, kind of distribute the a, distribute the b, and then regroup things according to like terms. So this will really, if we did that, we'll get x times a plus b plus, and then that'll be 2a minus 4b. Okay, and so that is the same as this, and so that has to equal 1. Okay, so the fact that this has an x in it and this one doesn't, that means a plus b has to be 0. And then a plus b is 0, so that'll make the x go away. But then this has to also equal 1, so that this ends up being 0 plus 1, which is 1. So now we'll do system of equations off to the side. So that means that 2a minus 4b has to equal 1. And a plus b has to be 0. Okay, I'm going to times both of these by 2 and then subtract. So those cancel. Negative 6b equals 1. That means b is negative 1/6. Make sure that, yeah. And if b is negative 1/6, that means that, oops, that should be b. That means a is positive 1/6, because they add up to be 0. Alright, so now this a is 1/6, and that b is negative 1/6. Okay, so let's go back to here. Let me rewrite this. A is 1/6, so this is really 1/6 times 1 over x minus 4, and here there should be a dx. This will really be minus 1/6 times 1 all over x plus 2. Okay, and then remember, integral of this is just ln of the bottom. This is really 1/6 ln absolute value of x minus 4. And the same idea with the next one, to be minus 1/6 ln absolute value of x plus 2. Okay, and then we'll integrate this from 1 to 0. Okay, and so now we can see why we need the absolute value, at least for this one, because when we plug in 1 and 0, we'll get negative values, and we don't want this to be undefined, since it's not undefined. Okay, 1/6, so now we'll start plugging in these values, so that'll be 1/6 ln 3, right? The negative 3 will become positive 3, and then that's minus 1/6 ln 3. Okay, so that'll be 0. Minus, now plug in 0. 1/6 ln 4 minus 1/6 ln 2. That's 0. This will just be negative. Pull out the 1/6. Pull out the negative 1/6. And keep in mind, this negative will distribute to make this negative and this positive. But so if I pull out a negative, I'm left with ln of 4. That should be minus ln 2. Okay, and you could leave it like that. You know, I'm going to simplify it just in case someone else does and you want to see. So that'll be, and then remember, when you subtract two logs with the same base, you divide their insides. So this will be ln 2, like that. It's probably the most simplified that you want to get. Okay, last one, for k equals 1. Okay, find the value of the integral from 0 to 2. Or show that it diverges. Okay, so this will be kind of like a new type of problem. Okay, so when k equals 1, integral from 0 to 2, 1 all over squared minus 2x plus 1. Okay, so the difference between this is that, here, we can rewrite this. Right, that's x minus 1 squared. Should I just write dx on the top? Okay, the problem with this one is this function's not defined when x is 1, and you can't take the integral over an entire function that has a vertical asymptote like that. So we'll have to split it up according to the vertical asymptote. So here we'll kind of be learning something new with this one. Okay, so if we split it up from 0 to 1, plus, and then the integral from 1 to 2. Okay, so think about how this function's working. Okay, so it has a vertical asymptote when x is 1. Let's say that's right there. And then a horizontal asymptote at y equals 0. And then it does one of these. This is 2, that's positive. This is like one of these volcano ones. Looks like this. Okay, so if you think about it, we want to find the area underneath this graph. So we want to find all this area and all this area. So the reason that they say or show that it diverges is because when there's a vertical asymptote, it could be that there's an infinite amount of area here and an infinite kind of amount, or it could converge to some number. This area could be finite or virtually finite because it converges to some number. Okay, but so what that means is, if you notice, look at this integral. This first integral is from 0 to 1. So we want to find all this area from 0, x equals 0, to 1. And so do you see how, I'm just going to kind of do it. We could do limit as, is it t or x? Yeah, we'll do t. Limit as t approaches 0 from the right, and the integral from t to 0, or sorry, t approaches 1 from the right, integral from 0 to 1 of this function. Okay, so think about what that is. So we're going to find the area. Oh, sorry, and this should be a t up here. T like that. That should be a t. So we want to know what's the integral when this t approaches 1, but from the right, which is really what this function kind of represents. If we want the area, we want to know all the area from 0 to some value as this gets closer and closer to 1 from the right. Oh, it should be from the left. What am I doing? From the left. Alright, so now we'll evaluate that in a second, and now we'll do the same thing. Limit as t approaches 1, now from the right hand side, and now we're going from t to 2. Yeah. Of this function. Okay, so now we see here we're going from t, some t value, to 2, somewhere here, finding all that area. But we want this, whatever this t value is, we want it to get closer and closer to 1 from the right hand side, and that's why we'll do this limit. This t now is going to be getting closer and closer to 1 from the right hand side like we want it to. Alright, so now we just have to evaluate this little expression. So first we'll integrate this, and this integral is not too bad actually. So just off to the side, if we do integral, this is really just negative x minus 1 to the negative 1. So negative 1 all over x minus 1. Okay. Okay, so now we know this is really limit. T approaches 1 from the left of negative 1 all over x minus 1 from 0 to t. Limit as t approaches 1 from the right, negative 1 all over x minus 1 from t to 2. Okay, now we'll evaluate each of these integrals by plugging in the limits. Okay, if you plug in t, you just get 1. If you plug in 0, you get 1, so that's just plus 1. Now we'll do the same thing. Plug in 2, you get negative 1, minus, that'll cancel out with when you do minus, it'll cancel out with that negative, and then just plug in t, like that. Okay. Okay, so as t approaches 1 from the right, from the left, that's values of t that are smaller. And so this will be a negative number. So this will, this is 1 over 0, so it'll approach infinity or negative infinity, and this whole thing will approach infinity. So this whole limit is infinity. Okay, the next one, t from the right, this is always positive when t is from the right of 1. So this is another positive infinity. So it's really plus 1, and then this is really minus 1 plus infinity. And this is kind of each of these. Okay, and then this just equals infinity. So that means that this whole limit, this whole integral, diverges. So therefore, integral from 0 to 2 of this function diverges. Okay, that was something new. Okay, so this one, just a review of a how to do a slope field for the first one. So you have all these 9 points here. Each is x and y, has an x and y coordinate, and all you do, here you have the derivative, right? And you're just going to plug each of these points in, x and y, in for the x and y here, and that'll be the derivative at that point, which is the slope of the tangent line at that point. And for each time you plug in a point and get a slope, you just kind of estimate that slope with a little segment. Okay, so we'll do that now. Alright, so maybe I'll do this above here. So the points are like 1, 0, 1, 1, 1, 2. Okay, so starts out with 1, starts out with 2, starts out with 3. Okay. Okay, so let's say you plug in 1, 1 into there, you get 0. Okay, plug in 1, 2, you get 1, 1, 3, you get 2. Okay, plug in 2, oh, whoops. Wait, what am I doing? Here, I made a mistake. And I erase this. Okay, first point should be 1, 0, I think. Okay, and that's undefined. Alright, and then now 2, 0. Plug in 2, 0. You get negative 1/2. Plug in 2, 1. You get oh yeah, okay. You get 0. Plug in 2, 2. You get 1/2. Alright, just making sure. 1/2, yeah. Okay, and then plug in 3, 0. So that's negative 1/3. 3, 1 is 0. And 3, 2 is 1/3. Alright, now we'll just draw all these and just estimate them. And an undefined slope is just a vertical line. So that at 1 comma 0, should make this a little thicker. 1 comma 0, there'll be that line. Oops. That line, so that's undefined. At 1, 1, the slope should be 0. At 1, 2, the slope should be 1. So that's like a slope of 1. That's a slope of 1. And just kind of keep going like that. 2 comma 0 should be negative a half. Anytime the y-coordinate's 1, it's always 0, so that's a slope of 0. And this should be positive a half. There, and then this is like a positive third and negative third. Something like that. Okay, so just something like that. Okay, let y equals f of x be the particular solution to the differential equation with the initial condition f of 3 equals 2. Okay, write an equation for the line tangent to the graph of y at x equals 3. Line tangent, okay. Okay, so we know at 3, f is 2, so the point is 3 comma 2. And then the slope, so we know if we plug in 3 and 2, you see up here, we get a third. We can just plug it in. And so that's the slope of the tangent line at that point. So slope is, what is it? 3 comma 2 is 1/3. Alright, and now we'll find the equation of the tangent line. So we'll start off with mx plus b. We'll plug the point and the slope. Like that. And then we can see b in this case has to be 1. Alright, so now our line is y equals 1/3 x plus 1. Alright, and then now we'll plug in 3.3 into that, and then that'll estimate the function at 3.3. So this is like 1/3 times 3.3 plus 1. 1/3 of 3.3 is 1.1, and that's 2.1. Okay. Make sure. Checking. 2.1, yeah. Okay. Okay, last one, find the particular solution with the initial condition. Okay. So now we'll start off with the differential equation that was given. So y minus 1 over x. Okay, so remember with these, most important thing is to separate the variables. Get all the y's on one side and all the x's on the other. And so we'll divide by y minus 1, and that'll put it in the denominator here, and then multiply by dx, and that'll put it in the numerator. Okay, so if we do that, get that. And then now we'll integrate both sides. This is ln. That's ln also. Okay, now we'll plug in the initial condition. So when x is 3, y is 2. So plug that in. Plug in 2, you get 1. This is ln 3. Ln 0, or ln 1 is 0. and that means that C is negative ln 3. Okay, so we'll plug it back into C here. That. Okay, we can do this different ways. I'm going to combine these using that rule of logs. When you subtract two logs, you can divide them. That. That. And then now, if, the only way that these two things equal each other, they're both ln's, is these insides have to equal each other. So we have y minus 1 has to equal x over 3. And that's it. And then just solve for y. Y equals x over 3 plus 1. Oh. Alright, that's weird. I think that's a coincidence. That came out to be the same as the equation for the line tangent at that point. Solution to the given initial equation, the initial condition. I'll have to think about that. Okay, but that's this is what it is anyways. Here, let me box it. Okay, so we got one of these where we're finding volumes of solids. Okay, so let R be the region in the first quadrant, bounded by the graph of y equals 1 over x, the horizontal line y equals 1, and the vertical line x equals e. So let's draw that real quick. I think everything's in the first quadrant that they're describing. Okay, and then we have, okay, there's 1 over x, something like that. We have x equals e. Like 2 point something, so that'll be, let's say, right there. First, oh, bounded in the first quadrant, okay. And then y equals 1. This one. Okay, y equals that. Y equals 1. X equals e. Okay, so we want to find that area. Okay, so now we see that this area is this top. We could do top minus bottom, and so the top, and we're going to do that from where these intersect, and these intersect when you could really set these equal to each other, which is really, this is y equals 1 and this is y equals 1 over x, and set 1 over x equal to 1, and you get 1, so that's this x. That's what this, that's where they intersect. And that's e. Okay, so this integral is going to go from 1 to e. And then the top line is 1, and the bottom line is 1 over x. All right, so that's what we have to solve. All right, so let's do this. So now we want to find the volume of the solid generated when that region is revolved around the line y equals 1. Okay, so anytime you're revolving a solid around a line, you'll use this formula. So remember, we'll do pi r squared, and here there's in between the line that you're rotating around and the area, there's no gaps, so this will be a disk method, and that's just this kind of integrating pi r squared from a to b, whatever that is. Okay, and this will be dx or dy depending. Okay, so now we just have to get what the radius is, and the radius is like of a cross section. And you won't do this always, but this will be the radius here, because that'll be like the radius of some circle, and this will be the other part of the circle, and then this comes up like this and then goes down. And that's like 3D. Okay, but really this radius is just the difference between the two. You know, this is just this upper function minus the lower function. Okay, so kind of the same thing, almost. So now we'll do the integral from 1 to e, same thing. And then pi here. And then the radius now is 1 minus 1 over x squared. And so we'll have to integrate that. Okay, first we'll FOIL this, I think. This will be 1 minus 2 over x. And then we'll just integrate each one of those separately. X minus x. I think that's right. Okay, so plug in E. Okay, ln of E is 1, so that'll just be minus 2. This will be minus 1 over E. I'll plug in 1. So ln 1 is 0, so that's 0, so this will just be minus 0 minus 1. I'll just do that. Is that right? Yeah. E, get that. Plug in 1. Yeah, okay. So we can see this whole thing, 1 minus 1 is 0, so this whole thing is just 0. And so this is it. So I would just leave the answer just like this. Okay, last thing. Region R is the base of a solid. Okay, so that same region is the base of a solid. For this solid, each cross section perpendicular to the x-axis is a semicircle. Write but do not evaluate an expression involving an integral that gives the volume of the solid. Okay, if we go back to here, let me erase some of this. Okay, so now, maybe I'll use a different color too. So let's say, so now they're saying each cross section is itself a circle. So like this is now a whole circle. We're not revolving anything. It's like now you have all these cross sections that each one of them is a circle. And that'll go throughout this whole thing. This will be a circle and then kind of come down. Okay, so whenever they describe the area, or whenever they describe a cross section like this, we're always integrating whatever the area of a cross section that they describe. Okay, so now a typical cross section, the area is going to be pi r squared for sure. We'll use pi r squared. What did they say, semicircle? Yeah, it's a semicircle. So actually, we really won't, I put these dashed lines here, but those shouldn't be there now that I see this. So there shouldn't be dashed lines. So it's just semicircles. Just these circles that go above the plane. Okay, and so now we need to get an area of one of these semicircles. Okay, so area of a semicircle in general is pi r squared over 2. And now we need to get that radius in terms of the function. So think about this diameter. The diameter of this is 1 minus 1 over x. So we'll divide that by 2 to get the radius. The radius is 1/2 times 1 minus 1 over x. Okay, and then if we combine those, we get pi, and then this squared is going to be times 1/4, 1 minus 1 over x squared all over 2. Alright, so that's the area. And then that we need to, oops. This, okay, so now, sorry, all right, so now that's the area, and then same thing, we're going from 1 to e, and then, you know, maybe it doesn't matter, you could just put this whole thing in there. You know, if you were gonna simplify, which you shouldn't really, this 1/4 and this 2 become a 1/8, so this is really pi over 8. And then you'll have a 1 minus 1 over x squared inside there. Okay, and that'll be, yeah, that'll be the expression. That would give you the volume, that volume that they describe. Okay. Okay, for this one, they say consider this differential equation, and then let y equals f of t be the particular solution to the differential equation, and then they want you to write the second degree Taylor polynomial for f about t equals 0, so kind of like a Maclaurin series, and then use that to approximate f at 1. Okay, so remember, second degree Taylor polynomial will be a Taylor polynomial where you know, t squared will be the biggest, you know, 2 will be the biggest exponent, basically. Okay, so remember with these Taylor polynomials, most important thing is finding the derivatives. Okay, so think about what we want. We want f at 0, we want f prime at 0, and we want f double prime at 0. Because the general form is fn, in this case it'll be at 0 times x all over n factorial. And this will be x to the n, like that. Okay. Okay, so we need, remember f of 0 is just the function, and then when n is 1, that's the first derivative. When n is 2, that's the second derivative. And then these are just plugging in the different n values. And we'll keep in mind this is n equals 0, n equals 1, n equals 2. Okay. And we'll definitely stop there. When n equals 2, this is x squared, and we know we want a second degree Taylor polynomial, so we'll stop when that exponent becomes squared. Okay, so each derivative, or f of 0, they give us as 8. F prime at 0, we can just plug in 0 for t, but you got to be careful because when you plug in 0 for t, there's no t's here. You know, but you can think of this as like this y here is like y of t. You know, just like that y is, you can think of as y of t. And then you can plug in 0 for t. You can plug in 0. So that's y of 0. And then y of 0, you know, f of 0 is really 8. So each of these y's really become 8s. Okay, so if those become 8s, this is really 8 over 8 times 6 minus 8. And that's 1 times negative 2, so that's just negative 2. Okay, so now we'll take second derivative. So here, so let me rewrite this down here, maybe. And I'm gonna distribute the y over 8. So we'll get 3/4 y minus 1/8 y squared. Okay, so we'll take derivative both sides. Okay, so keep in mind we're taking derivative with respect to t for both sides, and there's no t's, there's just y's, which are functions of t. So just remember, every time when we come to taking derivative of y, that's like dy dx, or y prime, or dy dt. Okay, same thing here. This will be like 1/4 y, and then times dy dt. Okay, so now we'll evaluate that. So we know dy dt is negative 2, and then y is 8. And so we'll just plug those in. 3/4 dy dt is negative 2. Y is 8. This is negative 2. Okay, so this will be negative 3 over 2. That'll end up being plus 4. Yeah, so that's negative 2 times negative 2. And then this is 5 over 2. Okay, so that's what this is up here. Okay, so now that we got all those derivatives, now we can write these out. Okay, so this is just going to be, so the Taylor polynomial is going to be 8, just the function. And then the next one will be negative 2 times x. The last one will be 5 over 2 times x squared. And then this is really over 2 factorial, like that. Which means this is 8 minus 2x plus 5/4 x squared. Oh, those should be t's. Okay, and is that all they wanted? Oh, and then use that to approximate f at 1. Alright, last thing is plugging in 1 into this. Okay, so this is 6 plus 5 over 4. That's 29 over 4. That's it. Okay, so last one. Which of the following is equivalent to that integral? Okay, definitely not. We'll just go through each of these. Definitely not that one. Integrals don't distribute to fractions, like to the top and bottom. Definitely not that. Okay, now for this one, I think these are going to be the same if this long division, if you do long division and you end up getting this, then they'll be the same thing. So I'm actually going to start with this and then change this to see if we get that. That seems easier to me. Okay, so really just means timesing this by 5 minus x. Because you'll do like negative 2 times 5 minus x over 5 minus x. You know, just to get a common denominator. And then this will be 2x plus 5 on the top. And then we get that. Okay, so those are the same. So this one checks out. And then the last one, I guess if we do u substitution, that if we do u substitution, then this whole thing becomes this somehow. Okay, so what should we make u? Definitely make u 5 minus x, I think. If u is 5, well, it's really what did they make u? U is 5 minus x. Plug those limits in, we get 1 and 3. But then we'll need to switch it. Okay, so let's see if this works. If we make that 5 minus x, that means du is negative dx. And then if we kind of rewrite this, this is x equals 5 minus u. Okay, times both sides by 2. You get 2x equals 10 minus 2u. And then add 5 to both sides. So now you get 2x plus 5 equals 15 minus 2u. And so now we got the kind of the 2x minus 5 that we need on the top. Okay, now we just start substituting everything. Okay, we'll do limits last. Okay, so the 2x minus 5 is the 15 minus 2u. The 5 minus x is just u. And then the dx is here is really, this dx is negative du. That's what we'll times negative du. Okay, and then now to plug in the limits. So these x limits are x equals 4 and x equals 2. And we can see if x is 4, u is 1. So that's the upper limit. And then if x is 2, u is 3. That. Okay, so that's not quite, so these limits are different. So now to get this limit to be the same as those, we can switch these and then change the sign, but this is already a negative, so we'll just end up making that positive. And then so that this negative just becomes a positive once we switch the limits. And then we'll split this up also at the same time. 15 over u minus 2u over u, which is just 2. Do we get the same thing? Yeah, okay. So these two are both, 2 and 3 are both equivalent to the original. Okay, and so that's it.